Okay. Yeah, so I'd like to thank the organizers for the invitation to talk at this wonderful conference. And sort of in keeping with the theme of this mini session, I'll talk about kind of dynamics in constrained quantum many-body systems. This is work done in collaboration with Sanjay, David Hughes, and Amos Chan at Princeton. And so, let's see. Right, so typically we characterize quantum chaotic systems by their energy level repulsion. And the generic belief is that for a many-body quantum chaotic system, the late-time dynamics resembles that of a random matrix chosen from, an ensemble consistent with the system symmetries. And so, for example, for an integrable system, we expect Poisson statistics, while for a chaotic system, we get Wigner-Dyson statistics. But there's a finer diagnostic that probes spectral correlations at all energy scales, and that's the spectral form factor. So that's the Fourier transform of the two-point correlation function. And here, W is the evolution operator up to some time step t, and E are the eigenvalues. So for example, for an n by n random matrix from the circular unitary ensemble, at 0 times you just get n squared, where n the Hilbert space dimension, and the spectral form factor behaves linearly up to the Heisenberg time at which it saturates. But if you have systems with locality, then at early times the spectral form factor deviates from RMT predictions. And if you also have systems with additional symmetries, then we only expect that random matrix predictions hold within a given quantum number sector. So, for example, here is kind of schematically the spectral form factor plotted as a function of time. And so for small times, a local system behaves like many decoupled systems, and so it deviates from RMT predictions. But at long times, once correlations have spread, it matches the RMT predictions. And the time scale at which the spectral form factor matches up with random matrix predictions is what we define as the Thales time. This is what's been done in the literature recently. And so, right, so Thales time is the time scale at which the spectral form factor matches predictions from RMT. And this is closely related to the nature of transport. So in a system with conserved quantities, typically the expectation is that RMT behavior will set in once all the conserved quantities have diffused. And so if you just had charge conservation, you would expect that the Thales time scales as L squared, where L is the system size. So the motivation for this work is to try to understand the nature of transport in constrained systems like Sanjay and John were talking about. So one example is these so-called fractonic systems where you have dipole moment conservation, which emerges, for example, in the presence of a strong electric field, as has been done now in Wasim Bakar's lab at Princeton. So one way to study the spectral form factor analytically is through these Floquet random quantum circuits, which are periodic in time and random in space. And for this, John Chalker's group has come up with a diagrammatic technique where the SFF can be computed analytically in a well-defined way at some large Q, which I'll define shortly. And if you don't have any conserved quantities, then they find that the Thales time scales as a log. Okay, so this is the random circuit that we consider. So we have a system where you have L site local gates U, where each of these U is has block diagonal structure. And at each site, we have both a spin and a color degree of freedom. And the spin degree of freedom is how we encode symmetries into the system, and the color degree of freedom is introduced to enable Haar averaging, and that's the analytic parameter that lets us do analytic calculations at large Q. And again, as I said, the SFF RMT behavior is only expected to set in within each symmetry sector, so you define it restricted to a particular global symmetry sector. So again, I'm not going to go into the details of how this is done, but there's a tractable way of evaluating the SFF averaging in the large Q limit, which was done by Chalker's group. And what it tells you essentially is that in the large Q limit, here, the spectral form factor can be given by, in terms of a bistochastic classical circuit, M. So M is basically, it has the same geometric structure as the initial circuit W that we started with, where you have these local gates. Except now that we've integrated over Q degrees of freedom, each of these local gates is non-random. And it's bistochastic, which means that its rows and columns all sum to 1, and it has the largest eigenvalue of 1. And so at late times, the spectral form factor can actually be expanded as follows. And what you find is that the Thales time then is just given by the gap of this classical Markov circuit. Okay. And this classical Markov circuit can be basically interpreted as the time evolution of some classical probability density. And so the Thouless time is basically given by the relaxation time of this Markov process. But this is also hard to study due to the structure of the circuit. But for gapless systems, there exists a continuous time approximation that we can use to estimate the gap of the circuit. And what we find in using this continuous time approximation is that you can map here P is a probability of finding certain configurations. And it's just given by this rate equation where H is a sum of commuting projectors, which is just given by 1 minus the local non-random circuit of the Markov circuit, local small m. And so in that case, the Thouless time just maps onto the inverse of the gap of this Hamiltonian that we've derived. And we can, and here numerically we test that the gap of this Hamiltonian H scales just like the gap of that Markov process M. Well, what's surprising and interesting is that the Hamiltonian that we end up is actually always of the Roxar-Kivelson type, where it's a sum of block diagonal projectors. So it's a frustration-free stochastic Hamiltonian, and it has a unique ground state, which is just a uniform superposition of all allowed configurations, C, where C are all the product states within a given symmetry sector, or more generally within a Krylov subspace in a Hilbert space fragmented system. And so then the eigenstates of this Hamiltonian are in direct correspondence with the relaxation modes of that classical process M that we started with. Okay. So just as an example, if we start with a Floquet random circuit with spin conservation, so just like we have spin a half per site plus the color degrees of freedom, we integrate out the color degrees of freedom, you end up with this classical circuit M, where each of the local gates has this form. And then once you take the continuous limit, we just end up with a ferromagnetic Heisenberg Hamiltonian. So you have emergent integrability in the large Q continuous time limit. And since this is an integrable system, we know what its gap scales like. We know the ground state just belongs to total spin L multiplet, and the low energy excitations are just spin waves. And so the gap, we can derive the gap for this. And since the Thouless time is the inverse of the gap, we get the Thouless time scales as L squared, which is consistent with diffusion. And we actually see that this happens even when we start with not just 2 site gates for charge conservation, but longer range gates or with higher spin systems. In that case, the RK Hamiltonian that we end up with is not integrable, but we still see diffusive behavior. Okay, so just to summarize this so far, basically for Floquet random quantum circuits, there's this quantum to classical mapping where you take the large Q limit and then the large T limit, and the Thouless time is essentially given by the gap of the RK Hamiltonian that you end up with. So then let's move to multiple conserving systems. So as Sanjay talked about, in these systems with dipole conservation, you get Hilbert space fragmentation, where within a given, if this is the circuit W, then we have all these different symmetry sectors. But now we actually have to restrict even further to some largest Krylov subspace because of this Hilbert space fragmentation. And there's a difference between weak and strong fragmentation, where a strongly fragmented system, the ratio of the largest subspace vanishes in the thermodynamic limit, whereas in a weakly fragmented system, this largest Krylov subspace in the thermodynamic limit is asymptotically equal to the size of the dimension of the symmetry sector to which it belongs. So here we'll only be concerned with weakly fragmented systems, and this happens for systems where you take a gate size L greater than 4. So this was shown by Frank Polman's group, for example, and we'll focus on weakly fragmented system with some largest conserved multiple moment M. And numerically, what we observe is, so the blue and red green dots are for charge conservation, and we see kind of diffusive scaling of the gap, which means diffusive scaling of the Thouless time. But for systems with dipole conservation, we see subdiffusive behavior. And we see this even for longer size gates and for higher spins greater than 1. So this suggests some kind of a universal reason for why we're seeing subdiffusive behavior numerically for systems with dipole conservation. So we tried to come up with a coarse-grained Hamiltonian. So you can derive a ground state wave function for this RK Hamiltonian and then take the coarse grain limit. And the ground state is just a uniform superposition of all allowed configurations. And so there's this procedure in this paper by Xiao Chen and company where you treat the spins as uniformly distributed random variables, and then the distribution flows to a Gaussian. And so this is the probability of a given spin once you take the coarse graining. And then in the continuum limit, you end up with the ground state wave function, which has this form. So it's some Gaussian, where rho is the density. And it has to satisfy a global constraint. And the global constraint is basically fixing the symmetry quantum number. And so global constraints are hard to work with. So we introduce height variables. So for each spin, you just define height variables on the links. If you have a charge conserving system, and if you had a dipole conserving system, you'd have the next height variable, which would be again on the sites, and so on and so forth. And then you can reinterpret these global constraints that fix the symmetry sector in terms of these height variables. So for example, for charge conservation, it's just given by the difference between the boundary height fields. And then for the dipole moment, again, it's given by the difference at the boundaries of these higher height fields. And then when we take the continuum limit, what we find is that the density is given by some m+1th derivative of this mth height variable. And the global constraint ends up turning into a boundary constraint on these higher height fields. And so for this ground state, you can also derive a coarse-grained parent Hamiltonian, and there's a couple of ways to do this. There's a regulator approach, or you can go the Fokker-Planck way, but I'm not going to go into details. You end up with the following Hamiltonian. I'll just jump to the end, where for the simplest case, a charge conserving case, you just end up with a quantum Lifshitz model. But more generally, you have these higher derivatives sitting in the parent Hamiltonian. And you can check that this annihilates the ground state that we derived. And so once you have this effective coarse-grained Hamiltonian for the system, it's straightforward to just look at its dispersion relation, and we find that the Thales time scales subdiffusively. So m is the moment that is conserved, and so for a dipole moment conserving system, the Thales time scales as L to the 4, and then so on and so forth. And since the Hamiltonian is invariant under an enlarged polynomial shift symmetry, the low energy physics is identical in all the symmetry sectors. And again, this is also what happens in the charge conserving system, which is more familiar, but typically RK Hamiltonians have some enlarged symmetry, and that's what we see here even in the low energy continuum limit. So just to quickly summarize this, started this analytic method for studying the spectral form factor in very general settings. So generically, if you have this Floquet random quantum circuit in the large Q late time limit, you can map it onto a classical Markov circuit, which you can then map onto this effective RK Hamiltonian. And then for multiple conserving systems, we derived an effective field theory, which predicts a subdiffusion for the Thales time. And this is consistent with the results from hydrodynamics that these papers also derived. So okay, with that, I'll also finish earlier and take questions if there are any.